Right, yesterday we had a look at torque, and that torque is the turning effect that a force has on an object. And normally it's an object which is fixed at one point called a pivot. So now we look at the whole reason why we are looking at torque in the first place, which is to look at how it affects torque on a coil. Okay? Right, let's move on. So, just to emphasise this, we have torque on a coil here. In a magnetic field, any current conductor will experience a force. What do we call this effect? Yes. The motor effect says that if you take a current conductor and you place it in the position where, in a place of space which has a magnetic field, it will have a force. If we place the conductor in a specific shape, like a circle, or if it's a rectangle is the most efficient, slightly curved rectangles, then we can use that rectangle to cause a twist. And we call this a coil. So what I mean by this is we're going to take a coil of wire, which goes in like this, we're going to bend it into a rectangular shape and come out. So this is the wire going in, this is the wire coming out, and it's able to twist and turn. Okay. This is the basis of a motor, and that's what we're getting our way up to looking at the motor effect as it applies to a motor. Okay. So, in a few more moments, we'll notice that because the wires in a coil run two in the same direction and two in another direction, only two of the wires actually have experiencing a force. The other two wires do not experience a force. So that's all that this is saying here. If we use a rectangular coil, then though there are four wires in the rectangle, two of them will experience a force, but two of them won't. Okay. Right, so here is the simplest setup that we call the setup of a motor. And we're going down the back in a few moments and we're going to have a look at how this will work. We need to supply a magnetic field. So here we are at the magnetic field. We have a north pole over here. This is a bar magnet. And a south pole over here, another bar magnet. Just remind yourself that bar magnets can't exist as a north pole or a south pole by themselves. So there is actually a north pole here and a south pole here. But because we orient the two magnets together, like this, most of the flux, the lines of flux, the field lines, the magnetic field lines, fly out from here and don't come back and around, but they go straight across. And I'm going to draw them in a light colour, so I'll draw them in orange going across. Okay, three enough. At the same time, we're going to put in a rectangular coil. So this is a piece of wire that's bent into the shape of a rectangle. You can't get a perfect rectangle, we can't close it at the ends because we've got to get the current to go into the coil. So we have this little part down here where the current has to come in and out of the coil. So the rectangle itself is this shape just here. And when you look at the direction that current flows in here, we'll just make sure current goes in this wire, so we're going to current in that direction. It will flow this way. It'll flow that way because it's a closed loop. It flows this way, and that way. Okay. Now I said before, because it's a rectangle, it has four sides. Two are parallel and the other two aren't parallel to each other as well. I said that two of the wires will experience a push or a pull, but the other ones won't. So let's find out which two wires get pushed or pulled. In other words, experience force. So let's have a look at, we'll start with this wire just here. See that one there? Current is going that direction. So we're going to use our right hand push rule, the FBI rule, and we're going to indicate that B is going, at this point here, B is going that way, I is going that way. Let's work out which way the force will go. So, putting our thumb pointing up, B pointing to the right hand, F is extended. What happens to this wire? Right, this wire is pushed into the board. Okay. Now, if this wire is pushed into the board, let's have a look at the other wire on the other side. Choose another colour. This one here. Oops. That one there. The current is flowing that direction on that side. So, looking at what happens here, I is flowing down. B is flowing in the same direction because we're not changing the magnets. So, making your thumb point down, B point to the left, to the right I should say, and your thumb out, a finger out. Which way does this come? This is out of the board. Okay. Looking at the two other wires. So this one here and this one here. I know that this has got a hole in it in this section here, but we're just going to assume it's a complete loop. So these two wires here, let's looking at the direction of current. Now the current on the top wire, this wire here, current is flowing that way, field is flowing that way. What do you notice about the current and the field's direction? Right, they're flowing together, and when two of your fingers are flowing in the same direction, what happens to the force? Right, there is no force. So on that wire there is zero force. The reason being is the wire is running with the field. The current runs in the same direction as the field. Similarly, in the bottom wire over here, the current is flowing against the field. But still in the same direction as the field is going. It's parallel to the field, isn't it? In just the opposite direction. It doesn't matter if it's running with the field or directly against the field. Is there a force on it? No, there is no force here either. There is zero force. Okay. So in our loop here, if we were to take our loop, here's our rectangular loop, then there is a force on this wire and there is a force on this wire. There are no forces on the other two wires. This wire here is pushed into the page and this is out. If we somehow make this able to be anchored and spin by putting in a what we'll call an axle or an axis, then what will happen will be this side gets pushed in, this side gets pulled out, then this becomes twisted. Does that make sense? Okay, just pause ourselves there and we'll go down to the back and have a look at this so far. Okay, so what we just saw down the back of the room was this situation here. This is the identical situation that we just had in the last slide. So here's the last slide. That's viewing this situation from above. This is in 3 dimensions. And 3 dimensions often give us a much better idea of how to do it. So this is the North Pole over here. This is the South Pole. There is our loop. We said that the current was going into the page here. So it's going into, so the current is going into that loop in that direction and out through this way. We said that the only 2 wires that experienced the force were this one and this one, because they're the ones that were cutting across the field. And we said that this one was forced down in this direction and this one was forced up here, causing a spin in that direction. Okay? And this is the basis of all modern motors. Motors that take electricity and convert it into motion. Okay? So here, in this case, it goes anti-clockwise. But as we worked out down the back, if you change either one of two things, we could change the north and the south pole, swap them over, or the difference of the current. If we change them, we can make this go the opposite direction clockwise itself. Yep. Now, the one thing we've got to get really into our heads is the force. This is looking directly side on again. And this little circle that you can see just here, that circle there and there, these are the two wires. These are the two wires that we see there and there. Okay? So we're going to look really straight down this here. And when you look down, you will see side on, this is the wire, and two little wires coming in. Okay, I'll just... Okay, you're seeing that part there side on and the two circles. Okay? So are you understanding what you're seeing here? So this is the coil in this position here. There's the horizontal coil. Okay? You can only see one wire on it because the other wire is behind it. Okay, so you're looking only directly side on. Okay, in the horizontal one, which is the original position, let's just call that. The horizontal one is that one there. Okay. So that's back in that position there. We have two forces, the force pushing out of the page and the force pushing down the page. That causes the coil to tilt, and it now tilts to this point here. Okay. Now, what is the force like as it tilts on the wire? So going back, all that will happen is this wire, this here, that one wire. It's just a wire which is running backward in space. So it's like this. It used to be horizontal. Now it's just simply moved up there. Okay? So it's moved from the horizontal position just to slightly higher than itself. Are we okay with that? What's the force like? If we have the formula F equals BIL, sine theta, firstly, is it changing its angle in the field? So I've got to find myself something which is straight and long. I'll just go for this. It won't go. So imagine that this over here, that's the left side of, is that your left side? The left side of the room is the north pole, and the right hand, that's the south pole, and that's the wire. Okay? Now, at what angle is it to the field? So there's the field that way. It's 90 degrees. Okay. Now, all this is doing is it's moving from here to here. Okay. What angle does it change the angle for the field? No. So the angle of this does not change from the field. So as that wire lifts itself up during the rotation, theta remains the same. The length of wire in the field, does that wire get shorter? Does it get longer? No. Is the current that it's in, that flowing through that wire, change as it goes up? No. Does the magnetic field, do I change the magnets as it goes up? No. So what happens to the force as this rises ever so slightly? It remains the same. So in this position, in the pink position, horizontal, we have the force which I've coloured as red. When it goes to this more bluey purple now, it's still the same force. Okay? When it rises to, what's my next colour on the entire orange, into the orange position, okay? What is the force like still on those end wires? It's the same. The force is the same no matter throughout the whole of that term. Why? Because the wire still is in the same orientation in the field. So the force on the wire remains constant throughout the whole of this quarter turn. It's only a quarter turn that we're looking at here. We understand that the force is the same. Okay. My question is, if the force is the same, is the torque the same? And so far I've already got a few. What did you say? No. Why? What's the thing that's the reason why? Yes, the torque does change, but why? Good, excellent. Torque is related to force, isn't it? Torque is FD times sine theta, where theta is the angle made at the ends, isn't it? So, though the force is the same, the torque goes from maximum at the where it's directly going horizontal there, to 0 at the top. And this is a bit of a problem. That means that if we design a motor that looks exactly like this, it's a really good motor if the coil is horizontal, but as it twists to the vertical, it becomes rubbish. The motor's rubbish. All the motor will do is do this. Go from horizontal to whoop, and stop. No, because they're always running with the field. So those ones there don't. No. I think I know. I think I'm answering what I'm thinking. I'm asking. Ask me a question again in a few moments. It might make some more sense. I don't know if I just answered the right question for you. Okay. So torque is 0 at the top. Torque is maximum in the horizontal. And that's our problem. It's a really bad design for a motor. Okay. So let's have a look if we did have the motor running in these three directions. This is a diagram from page 13 of your book. Okay. Okay, now please notice that the order of the things is 1, 2, 3 going right to left. Okay. This is what you see directly over here. The diagram, the three-dimensional diagram, shows the position of number 2. And this is the coil has turned, and that's the coil there, and seeing it side on again, and it's turned at an angle theta to the field. Now we know the torque is maximum here. And torque is 0 here. Why is it maximum at the top one? Good. The angle here is 90 degrees. Okay. So this here is that the angle is 90 degrees. Now, what we need to do is look at an easy way of working and reckoning this angle. This angle is the hardest thing that we're going to reckon. Now, here, there is the angle. Is everyone okay that that is angle? Okay. So theta is getting larger. Therefore, torque is lessening. Lessening. Okay. Until theta here is 180 degrees. Okay. And this is measuring theta as the direction between the force. These arrows are the force arrows, and the direction of the distance there. Okay. So we're measuring the angle here as the angle. But in a few more moments we're going to realise that it's going to be too hard to try and measure this angle, because what will we be measuring against? We're going to be measuring against an invisible field. So what we're going to try and do is, can we measure another angle? So let's rub that out there. And you'll see that if we measure the angle, there is the coil going along there, and we measure the coil's tilt towards the field, then as theta, then that might be an easier angle to measure, rather than this angle up here. Now, is there a way of reconciling these two angles together? Well, if this up here, we'll say this is alpha, and it's that angle there, and that angle there is theta, what is its relation? So I'll rub that out and make it a much nicer diagram. So let's put in firstly that's our coil. That's the angle that we're going to be measuring in a few more moments, and that's the old theta that we used to measure. Okay? So, dropping it down perpendicular there, this is 90 minus theta. Okay? So 90 minus theta and what is it? Sorry? It's the exterior angle, isn't it? So what's this in terms of theta? Sorry? So you're all saying it's too soft. It's theta plus 90, isn't it? Okay? So it's theta plus 90. Now I want you to just check for me. Just do sine 20. And cos 110. Okay, what are they in relationship to each other? Right, they are the same but opposite. Okay. So if we were to use a cosine rather than an angle as the sine angle, so rather than using that angle up there as theta, we'll use this angle here as theta and use the cosine, we'll still be measuring that one up there with you. Okay? So if I measure this here as 30 degrees, that would mean that this up here is 150 degrees. Okay, are we okay with that? And if we use the cosine rather than the sine, it is automatically taking this. And also, if we make sure that the angle is less than, that we measure is less than 90 degrees, so we only take angles up to 90 degrees, then we'll get a positive number. So we won't have to worry about that cosine goes negative in the second quadrant. So we are going to, in a few more moments, change from using the theta, measuring it up there, by measuring the angle between the tilt of the coil and the field, and using cosine instead of sine. That's all we're going to do. Are we okay with that? So we're just changing it ever so slightly to make it easier for us. So I'm going to try and derive this formula for you, not derive it so much as just get you an idea of it. Okay? So let's firstly work out how to do the torque, and I'll just very rapidly go through this. If you don't get it, don't overly worry. Here is our coil looking side on. Here is the same coil look from above. Are we okay? We know that torque equals force times distance. Okay? And the distance is that length just there. Okay. So we are going to work out the force on this wire. Now let's give ourselves the length up here. We'll call this that length there L. Okay? And this distance here is D. Are we okay with that? Okay. Now the force on this wire would equal BIL, at the moment it's sine theta. We're going to change that to cos theta in a few moments, you'll see why. Okay. Now, that means that this equals BIL sine theta. Now we need to multiply it by D. Times D, because that's F times D. Now, BI sine theta LD, when L multiplies by D, it's the area of this half of the rectangle. Are we okay with that? So far, okay with that? Now, is there one force, one torque on this coil, or is there two? Two. So it would be another torque going up the other side here, and they'll be adding together. So we'll have two forces here, but I'm just going to do it. That would then mean that we have another LD over here, and that LD will give you the area of the other half of the coil. So all up, we'll be measuring the area of the entire coil, which is this here. If I have 2 wires, 3 wires, or 4 wires, then at the moment I've got 2 of those, because I've got 2 torques. But if I've got this wiping around more than one time, every time a wire wraps around, because we're not going to have a rectangular coil just made of a single wire, we'll wrap wires around, we'll get the equivalent number of extra forces, wouldn't we? So we're going to change that from 2 to an N. And we measured a few moments ago that it was easier to measure with the cosine of that angle if we're measuring, rather than the angle here, that we measure the angle with the coil. Okay? So we come up with N. BIA, there's the A, and rather than using sine theta, we use cos theta, where theta is no longer the angle up here, but the angle that we tilt the coil. Okay with that? So, that being derived, let's work out what everything was. N, the number of loops in the coil. BI, you know, I'm not going to tell you about that. A is the area of coil. No, you don't, because that's for every one loop there is two torques. So it automatically divides it by 2 again. Okay? So you're halving the same. So if you get 4, that's 2 loops. Okay, so you're doubling at the same time as then halving. Okay? So the area of the coil, theta is the angle the coil makes. It's the angle the coil makes with B, the magnetic field. Before, with the motor effect formula, theta was the angle the wire made. But we're not going to measure that anymore. We're going to measure the actual coil, because it's easier to measure an entire object than a single wire within that object. Are we okay with that? So now we can actually use this to work out the torque on the coil. So here is the problem. It's a coil which has an area of 5 by 4. It has 15 windings. Okay, 15 windings means there are 30 wires. Okay, so that's already doubling and then halving. Does that answer your question there? Okay. It's placed horizontally in a magnetic field with a strength of 12 Tesla. So let's just have a look at it side on. This is north to south, and here's the coil side on. The angle it makes here is 90 degrees. So it's making 90 degrees with the field. So now, I said before that theta, sorry, I put 9 degrees there before the announcements happened. Theta is not that angle there. That would be the angle that the wire is making the field. So, I'm just going to write that out because that is so misleading. The magnetic field is this way and the coil is this way. What angle is made? It's theta equals 0 degrees. Okay? It's 0 degrees with the field. Okay? If it was to be tilted, then the tilt would be that angle there. Okay? Right, so let's just do it. T equals N, the number of windings in the coil, the number of times the coil is wound around. It gives, for every wound piece of wire, you get an extra piece of torque. So there are 15 windings. Times B is 12 Tesla. Times I, the current, what's the current? Let's give current a value. Let's make I equals 2 amps because I haven't got it there. I must have roughed that up. So times 2, I made that up. Times area. Now area, what's the problem with 5 centimetres and 4 centimetres? Right, they need to be in metres, so it's 0.05 times 0.04 and cos 0. Cos 0 is 1. That's the reason why it's maximum in the horizontal. Putting that together, what value do we get? Because I just put a 2 in there. 0.72 Newton meters. Okay? Okay. Are we okay with that? Claudia?